Control of respiration. The nervous system controls the rate of the ventilation by adjusting the rate and depth of breathing in order to meet the demands of the body. Thus, arterial blood oxygen concentrations and carbon dioxide concentrations are commonly altered, even during strenuous exercise. The respiratory center. The body's respiratory center is composed of several widely dispersed groups of neurons located bilaterally in the lower portion of the brainstem, the pons and medulla oblongata. The respiratory center is divided into three major collections of neurons. The dorsal respiratory group plays a fundamental role in the initiation of respiration. It is also a primary generator of the rhythm of respiration, serving to maintain regularity of breathing frequency. The ventral respiratory group of neurons has several important functions. First, respiratory signals from these neurons contribute to the respiratory drive for increased pulmonary ventilation. Second, stimulation of some of these neurons in the ventral group causes inspiration or expiration depending on where the stimulus is located. The neurons are especially important in providing the expiratory signals to the powerful abdominal muscles during the more forceful expiration. And the pneumotoxic center controls both the rate and pattern of breathing. The primary effect of this center is the control of the duration and filling cycle of the lungs, the limiting factor in inspiration volume. This effect increases the rate of breathing because limiting inspiration shortens expiration and the entire period of respiration. Cardiovascular and respiratory response to acute exercise. The effects of exercise, both acute and chronic, on cardiovascular and respiratory functions significantly influence the anatomical and physiological parameters previously described. A basic knowledge of those responses is essential. These responses are discussed here, beginning with the acute response and followed by the chronic effects of training. Acute and chronic response of the heavy load resistance work are differentiated, whereas possible from responses to more repetitions of light loads with less rest. Cardiovascular response. The primary function of the cardiovascular system during aerobic exercise and some types of resistance exercise, greater repetitions with lighter loads, is to deliver oxygen and other nutrients to muscles. The section describes systematic mechanisms of these acute responses. Cardiac output. The amount of blood pumped by the heart of the cardiac output is determined by the quantity of blood ejected with each beat, the stroke volume, and the heart rate of pumping. Q equals stroke volume times heart rate, where Q is the cardiac output. Stroke volume is measured in milliliters of blood per beat, and heart rate is measured in beats and contractions per minute. Cardiac output is usually expressed as the volume of blood either in liters or milliliters ejected per minute. Aerobic exercise is in progression from the rest of the steady-state aerobic exercise. Cardiac output initially increases rapidly, then more gradually, and then reaches a plateau. With maximal exercise, cardiac output may increase 4 times the resting level, about 5 liters per minute, to a maximum of 20 to 22 liters per minute. Stroke volume begins to increase at the onset of exercise and continues to rise until the individual's oxygen consumption is at approximately 50% to 60% of maximal oxygen uptake. At that point, the increase in stroke volume begins to plateau. College-age men have maximum stroke rate volumes averaging between 100 and 115 millimoles of blood per beat. Maximum stroke volume for college-age women are approximately 25% less, owing to smaller average body size. Resistance exercise. Heavy resistance exercise is associated with no comparative change or only small increases in cardiac output, that which is observed in primary due to increased heart rate. As a load is reduced and repetitions increase over longer, cardiac output may respond more similarly to that observed with aerobic exercise, although generally to a somewhat smaller degree. Stroke volume. 2 physiological mechanisms are responsible for the regulation of stroke volume. The first is a consequence of the end diastolic volume, or volume of blood available to be pumped by the left ventricle at the end of the filling phase, or diastole. The second means is through the action of epinephrine and norepinephrine, hormones of the sympathetic nervous system, catecholamines, which also produce a more forceful ventricular contraction and generate greater systolic emptying of the heart. Aerobic exercise. With aerobic exercise, venous return, the amount of blood returning to the heart, is increased, and thus end diastolic volume is significantly increased. With the increased volume of the myocardial fibers becoming more stretched than at rest, which results in a more forceful contraction, that is, an increase in force of systolic ejection and greater cardiac emptying. This phenomenon, the Frank Starling phenomenon, described in former terms, states that the force of contraction is a function of the length of the fibers of the muscle wall. Furthermore, this increase in cardiac emptying is characterized by an increase in ejection fraction of the end diastolic volume ejected from the heart. In addition, and also at the onset of exercise, or even with the anticipation of exercise, sympathetic stimulation increases myocardial contraction and consequently increases stroke volume. Resistance exercise. As with cardiac output, the intensity of the effort of resistance work is important to the acute response of stroke volume. Heavy resistance work is associated with no change in stroke volume or even a decrease in the value. Particularly, very high intra-abdominal and intrathoracic pressures develop during the lift, limiting venous return and thus reducing end diastolic volume. Superimposition of the Valsalva maneuver, straining against a closed glottis, can further elevate these pressures and further limit venous return. See Valsalva maneuver, page 126. As load is reduced, the response again can become more similar to that of aerobic exercise. Respiratory responses. Aerobic exercise provides for the greatest impact on both oxygen uptake and carbon dioxide production. Significant increases in oxygen delivered to the tissue, carbon dioxide returned to the lungs, and minute ventilation, the volume of air breathed per minute, provide an appropriate levels of alveolar gas concentrations during aerobic exercise. With aerobic exercise, increased minute ventilation occurs as a result of increases in the depth of breathing, frequency of breathing, or both. During strenuous exercise, the breathing frequency of healthy young adults usually increases from 12 to 15 breaths per minute at rest, 35 to 45 breaths per minute, while tidal volume, the amount of air inhaled and exhaled with each breath, increases from resting values of 0.4 to 1 liter as much as 3 liters or greater. Consequently, the minute ventilation can increase from 15 to 25 times the resting value, or to values 90 to 150 liters of air per minute. During light aerobic exercise, there is an increase in ventilation, which is directly associated with both increased oxygen uptake and carbon dioxide production. In this instance, the increase in ventilation is primarily due to the increased tidal volume. The ratio of minute ventilation to oxygen uptake is termed ventilatory equivalent and ranges between 20 and 25 liters of air per liter of oxygen consumed. In more intense exercise, generally above 45 to 65% of maximal oxygen uptake in untrained individuals and 70 to 90% in trained athletes, breathing frequency takes on a greater role. At these levels, minute ventilation rises disproportionately to the increases in oxygen uptake and begins to parallel the abrupt rise in blood lactate. At this point, ventilatory equivalent may increase to 35 to 40 liters of air per oxygen consumed with this high-intensity activity. With inspiration, air enters the gas exchange area, the alveoli. However, with inspiration, air also occupies areas of the respiratory passage, the nose, mouth, trachea, bronchi, and bronchioles. This area as a whole is not useful for gas exchange and is called the anatomical dead space. The normal volume of this air space is approximately 150 milliliters in young adults and increases with age. Because respiratory passages stretch with deep breathing, you should recognize that anatomical dead space increases as tidal volume increases. Nevertheless, tidal volume increases relatively more than that of the anatomical dead space, resulting in a lesser percentage of tidal volume as a component of the anatomical dead space. Thus, increasing tidal volume typically provides for a more efficient ventilation than simply increasing the frequency of breathing alone. Physiological dead space refers to the alveoli, in which poor blood flow, poor ventilation, or other problems with alveolar surface impair gas exchange. The physiological dead space in the lungs of healthy people is usually negligible because all or nearly all alveoli are functional. Certain types of lung disease, chronic obstructive lung disorder, pneumonia, however, can significantly reduce alveolar function. Increasing physiological dead space by as much as 10 times the volume of anatomical dead space. Gas responses. The movement of oxygen and carbon dioxide across a cell membrane, diffusion, is a function of the concentration of each gas and the resulting partial pressure exerted by the molecular motion of each gas. Diffusion results from the movement of the gas from a high concentration to low concentration. At the tissue level, where oxygen is utilized in metabolism and carbon dioxide is produced, the partial pressure of the